or confirm if you can hear me, right? Okay, thank you so much, and thank you for confirming that. I want to welcome you to my lecture today. But before I get started today, uh, I want to notify you that I've already posted midterm one makeup, and immediately you submit. Of course, you're going to see your results because that's already programmed. And like I said, you only have like 60 minutes the moment you start. But I think I leave that open for some days. But the moment you start, your time is going to be running out. And after 60 minutes, of course, you automatically be logged out. So the moment you see results, I have not programmed the weights yet. I'm going to say it again. When you see your results, it may not have any effect on the overall result that you have because I've not programmed it. You know why? Because I first want to see whether you're going to have an improvement. Okay. Okay. So I want to welcome you once again to my lecture today. On Monday, we started continuous probability distributions, but we did not finish that material. And because of that, I promised I was going to start from that material today. So I've we started what we call continuous probability distributions, and of course, I've walked you through uniform. We're working on normal distribution. Of course, the uniform distribution is a distribution that we use when we assume equal chance to the outcomes. So which means when outcomes are equally likely, okay? I think I gave an example of, picking from, when you roll a coin, what is the probability of head showing up or tail showing up? Of course, that would be equal. Okay. So, and in real life practical situation, because the most simplest distribution uh, under the continuous probability is uniform. Because of that, we normally use uniform as a point of reference. Okay? Because, with uniform, we're assuming equal chance. So because of that, we use it as a point of reference. I remember I walked you through on Monday with the probability, architecture of uniform distribution. I also walk you through how to derive the mean and the variance, okay? And of course, how to solve a problem with a uniform distribution. Okay, so from there we move to normal distribution. The normal distribution is, I'm actually going to say, is the best distribution in statistics. When you have your data set, and if the distribution of your data set, okay, is symmetric in such a way that when you look at the center, right, and you look at the other halves, they are equal. For instance, it's like looking at me now. If you like, you partition me into two, okay, the halves, they're going to be equal. Does that make sense? That's what we call symmetric. And of course, the statistical architecture of that is what you see. We got two parameters in uniform distribution. If you want to conduct statistical inference with with normal distribution, we got two parameters. Of course, we also got two parameters in uniform. The parameters in uniform is A and B, minimum and the maximum. You know that, right? But in normal distribution, the parameters are mean and variance, which we actually call mu sigma squared. And what I'm displaying to you now is the statistical architecture of a normal distribution. And the state space is from negative infinity to positive infinity. Of course, I show you this the other time, like in when you talk about the two parameters in a normal distribution, what do they really capture in real life? I'm going to say that again. The two parameters in the normal distribution that I call mu and sigma squared, what is their role in real life? I'm going to say mu is the center. If I really want to get a center of a data, and if I want to talk about spread, of course, when in a stochastic environment, where when you take measurements, even using the same equipment, there's going to be variations. Okay. If there is no variation, we don't need center. If there's no variation, we don't need average. But because there's a variation, we find the average. And how can we actually trust our average? Because the average is to represent the other data point. If I really want to know how reliable is the mean, is the average, then I need to know the spread, how my data set spread out. Okay. And that is why in that situation, if I want to know how it's spread out, then I need a standard deviation. Okay. Which is what I'm actually displaying to you now. Okay. And of course, I walk you through, different, we can have a situation where we got three sets of data and the three of them have the same means, but they got different standard deviation. And I also walk you through situation where they actually have different means, but the same standard deviation. Okay, so we have data set like that, and I walk you through the properties of a normal distribution. I remember I actually also walk you through on Monday. How do we actually obtain the mean and the variance of a normal distribution? I think I walk you through how to derive the mean. And of course, you can also derive the variance as well. But let me tell you this. What is new is because when you look at the statistical architecture of a normal distribution, it's complex in a way. This is what I'm trying to say. If you take a look at this guy, looking at that function is kind of complex. But do you know we can actually standardize? The idea of standardize, like for instance, if I want to find a probability of data set that follow normal distribution, I'm going to say that again, because the reason why we need to figure out the probability distribution of data set is because I need that to be able to, compute my probability. If I cannot identify the right probability distribution, that may be difficult for me to find a probability. Now, let's say data set follow normal distribution, and we basically want to figure out the probability. Okay, instead of me to work with this density, I'm actually going to work with a standardized one. I'm going to give you an example now because the way I learn my statistics, the way I learn mathematics, I actually I relate to real life. I want to see what I'm learning. If I don't see it, it doesn't make sense to me. Now, let's say, for instance, I'm talking about scores of students, like you've done midterm 1. I have your scores. Those scores are not the same, right? They varies, right? They varies, and that actually reflects stochastic environment that we expect variation. Now, if I plot the histogram, because if I want to know the distribution of your scores, I need to get the histogram, okay, to be able to see whether it is symmetric. or not. Let's say that follow normal distribution. So, which means the probability distribution of your scores follow normal distribution. If I know that now, then I will be able to, I can answer a question like, given the average of your score, like everybody's score, and the standard deviation of your score, I want to find the probability that somebody choosing at random in this class will score more than 90, or will score less than 90, or will score between 80 and 95. If I want to do that, then I need to use a standardized version of a normal distribution. Does that make sense? That is the reason. Now, because of that, I'm now presenting to you the standardized version. Now, when X follow normal distribution with the mean mu, the standard deviation sigma, then I'm actually want to define a random variable Z, which is going to be, I'm actually going to subtract the mean I'm actually going to be subtracting the mean from each of the score divided by the standard deviation. Now, this is what I'm trying to say. I already know your score, right? Let's say if you are 20 in this class, I'm actually going to have 20 different scores, right? I'm going to have 20 different scores, right? If I have 20 different scores, I can find the average. I can find the standard deviation. Where am I using mean to find the average? Despite the fact that I know there are 3 measures of Sarah. What are the measures of Sarah? Mean, median, mode. Why do I go for mean? Why not median? Why not mode? Because the distribution is normal. If the distribution of data set is normal, if I want to get the average, I will use mean. I'm not going to, mean is going to be most appropriate. I'm going to say that again. When the distribution of random variable is normal, if I want to figure out the average, I'm actually going to compute the mean. If I want to know the spread, I will compute the standard deviation. But let me tell you this. What if in a situation where I plot my histogram and it is not normal, maybe it is skewed, either to the right or to the left. If I want to figure out the average, using the mean will mislead. Then it's either I use the median or I use mode. But how do I now measure the spread? In that kind of situation, I can no longer use standard deviation, but I can use what I call interquartile range. Has anybody heard about interquartile range? Okay, statistics more or less like a story. Now, what I'm trying to say now, if I want to answer a probability question, that has to do with data set that follow normal distribution, then we need standardization. Okay, which means Z is a standardized value. Do you know the essence of that Z? The essence of that Z is to bring everybody in the class to the same level. Initially, the X there's a lot of variations. And what is going to be the mean of the Z? Z will now follow a standard normal distribution with the mean 0 and the variance of 1. Okay. Now, if I now want to rewrite the complex architecture of a normal distribution, then instead of me to write that in terms of X, then I'm going to write that in terms of Z, in terms of that, which means I've already plugged in mu to be equal to 0 and the sigma to be 1. Then I got a new distribution that I call the standard normal distribution. Now, let's take a look at this. In a standard normal, which means if I want to find, give me 1 second. Now, if I want to find the probability of S greater than 85.5, maybe 85, you know what I want to do? If I want to find the probability that somebody in this class score more than 85 in the test, okay, do you know what I'm doing? Then I need to find the probability of Z greater than something, which means it's going to be 85 minus the average of everybody in the class divided by the standard deviation. So whether I'm talking about greater than or less than or whatever, you know, the sign here must agree with that. So that's exactly what I mean. So when you take a look at that, I mean, be interested in Z less or equal to A. What is the probability of somebody, you know, Z less or equal to A? If you take a look at it, Z less or equal to A is going to be the other part, right? So take a look at that. And if I'm interested in the probability of Z lie between A and B, it's going to be the probability of Z less or equal to B minus Z less or equal to A. I'm actually going to start with the upper point, then before the lower point, then I'm going to subtract them. If you take a look at the first one, the probability of Z less or equal to B, you see that, right? Okay, so that is what you see now. Less or equal, the Z less or equal to A, the unshaded, that white side, there's the white side. Z less or equal to B, the whole thing up to B. Okay, you can see that now, and which is basically going to be, if you want to find the probability of Z lie between that, and let me also tell you this, the probability of Z greater than A is going to be 1 minus Z less or equal to A. That is more or less like a complement. If Z is greater than A, what is the complement of Z greater than A? That will be less or equal, and they are mutually exclusive. And of course, you can see this guy. So that is Z greater than A. So take a look at that. Okay, so I think I gave different form of that for you to be able to see. And you know, the center you have to be 0, because the center of a standardized normal distribution is 0. Don't forget, the center is going to be 0, and of course the standard deviation is going to be 1. So if you see that now, that is Z less than minus A and Z greater or equal to A. Okay, and let me tell you this: if I want to find the probability of Z lie between A and B, it's the same thing as all this, because we're talking about continuous. It is not going to be the same when X is discrete, but when it is continuous, basically going to be that. Okay, so and so on like that. Now let us now go into an example now. Okay, suppose that Z follows standard normal distribution. Let me tell you this: there's a difference between normal distribution and standard normal distribution. The standard normal distribution is a special form of a normal distribution. Okay, we got a standard normal distribution when you plug in 0 for mean and when you plug in 1 for variance. Now, and that is why you see the standard normal distribution, you know, follow, you know, we have a mean of 0 and that. Now, they want you to find, if you take a look at question A now, you want to find the probability of Z less or equal to 1.05. If you want to find that, then we need, you know, in this course, we're going to use a statistical table. Has anybody seen statistical table before? In the statistical table, we're actually going to have Z table, we have T table, we have F. Okay, I think I'm going to bring one to this class probably on Friday for you to see. Now, I want to get the probability of Z less or equal to 1.05. Okay, all what I just need to do is to go to that table. When I go to that table, I'm going to check under 1 under 5, 1.0 under 5. Okay, I will have the value. It is in the table. Okay, for those of you who use R software,
This is P norm. If you do P norm 1.05, it's just going to give you a result. But since we're not using R, we're not using software here, we're going to be checking from statistical table. Okay. Now, if I want to do Z lie between that and that, okay, so I'm actually going to use this principle, which is going to be, I'm going to start with the upper one minus the lower one. Take a look at that. I'm going to be using that principle. Okay. So that is what, so is there anyone who doesn't really understand how to solve any of that? Is there anyone? Is there anyone? Okay. Now, I think I've explained the standardization now. Look at example 6.6. Suppose that X follow normal distribution. Now, this time around, we're starting from a random variable X. Okay. You started from random variable X, and it is X that follow normal distribution, okay, with mean 1 and the standard deviation 0.5. Take a look at that. And it's asking you to find the probability of X lie between 0 and 1.5. So what do I need to do first? I need to first standardize, because you have a random variable S that follow normal. It doesn't follow standardized. Then we need to first get Z. We use that, right? So we're going to first get the upper one. Okay, the upper Z, that will be 1.5 minus 1 divided by 0.5. Okay, I think this is going to be 1. Okay, then I'm going to get the lower one. So which is going to be 0 minus 1 divided by 0.5. So minus 1 over 0, I think minus 2. Now, the first Z give 1. The second Z give this. So what I'm basically going to do now, okay, when I have something like that, so this is going to be the same as the probability of Z, okay, lie between -2 and 1. If the X lie between that after standardizing, then I'm going to be equal to that. You're going to follow that same pattern. So, and this guy now can be broken down. Okay, if I want to break this down now, I'm basically going to say, okay, Z less or equal to, I'm going to start with the upper one, minus Z less or equal to -2. Okay, so I'm going to check this from the table. I'm going to check this guy from the table. Then I'm going to subtract them. That is exactly what I'm going to do. Is there any question on that? Is there any question on that? So that is the way that is done. Okay, so look at another example. Okay, you are given the mean. You have a suppose Y. Let me tell you this. The only way to know whether in your question they've already standardized, the only way to know whether they've already standardized is when mean equal to 0 and the standard deviation equal to 1. The moment it is nothing like that, then that has not been standardized. Like for instance, take a look at this guy now. Y follow normal with negative 2 as the mean, the standard deviation of 5. The first value is always the mean. The second value is always the standard deviation. So, which means I need to standardize that before. So if I now want to standardize now, I need to put into consideration that guy. Okay. Now, what I mean now, I want to find the probability of Y greater than 0. If I want to find the probability of Y greater than 0, okay, I will suggest that you do the probability of Y less or equal to 0. Because in the table is for less than. Does that make sense? The table you want to check from, answer question of less than. But if they ask you greater than, then you need to, for us, use the law of, you need to use a complementary law where you're going to say 1 minus that. So what I'm going to do now, I need to standardize using y minus the mu over sigma. What is and y is going to be 0 minus, what is it mean? Minus 2, which is going to be that divided by that. I think I'm getting 2 over 5 here. Okay, which is 0.4. Okay, so which means the probability of y greater than 0 now is automatically going to be z greater than 0.4. Okay, this guy is now this guy now, which is going to be equal to 1 minus z less or equal to 0.4. So all what I'm just going to do is to check this guy from statistical table. Then I'm going to subtract from 1. For those of you who use a software, R, if you use R software, it's basically going to be P norm is 0.4. Then you subtract that from 1. So basically, you're going to get a result. As easy as that. Okay. Now, the next thing I want to talk about inverse normal distribution. What do I mean by inverse normal distribution? You know, what have we done? What are we doing here? What we've been doing here, we are finding probability, right? We're finding probability, right? And we're checking from statistical table, right? The inverse normal is more or less like they've given you the probability now. Maybe you want to figure out the score. That is inverse. It's like, you know, in an equation, when you in an equation, now when you have 3x plus 5, right? If they give you the values of x, you know, you can find y. What of in a situation where it's okay, find x? That's an inverse. Like you want to solve for x. Does that make sense? So that is actually what we mean. So, like for instance, take a look at this. Find the probability of z less or equal to k equal to, that is 0.0778 is what they have checked for you in the table. You know, that is what we've been doing. Like we want to figure out the probability, right? But right now, the probability value has been given. They now need you to figure out what was the value of the z. Okay, so if you want to figure out, you know, that guy now, okay, which means initially, this is what you have. Initially, you got this x minus mu over sigma, but I'm interested in this guy. I need to solve for that. When I solve for that, my x is basically going to be mu plus z sigma. That is why you see sigma z plus mu, because the interest is actually on that. So if you now want to solve the problem now, the probability of z less or equal to k, okay, equal is 0.078, okay, then it means I will now need to go to the table. I will be looking for this guy. What do you think I want to figure out? I want to figure out the corresponding z-score. Because before I will go into statistical table, before I need a z-score, right? But right now, I'm going back to the table to locate the probability. When I locate this probability, this value, then what is the corresponding z-score? You know, in R, that is going to be Q norm. It means we are looking for quantile. Q norm. Okay, so you can follow all of that. Okay, now, according to empirical rule, if data set, how do I know if data set follow normal distribution? One of the way to know, apart from constructing the histogram, 68% of the data set will lie between one standard deviation. 95% of the data set will lie within two standard deviation. And 99.7% will lie within 3 standard deviation. That's what we mean by empirical rule. Some of you may be wondering, how do we get that? I'm giving you as an exercise to turn in for extra credits. If you have not applied your extra credits before and you want to apply it to the midterm, please let me know. Okay, now, f of x is 1 over square root of 2 pi sigma squared exponential raised to power this x minus mu over sigma all squared. How do they arrive at 68%? Okay, they arrive at 68% when I integrate this guy here. When I integrate this guy, okay, from mu minus sigma to mu plus sigma, because when you say within 1 standard deviation means mu plus or minus sigma. So when I integrate this guy, it's going to give me 0.68. I need somebody to integrate this and show me that the result is going to be that. That's how they arrive at 68%. How do they arrive at, the 95%? Okay, they arrive at 95% if I have integral mu minus 2 sigma, mu plus 2 sigma, 1 over square root of 2 pi sigma squared exponential raised to power that x minus mu over sigma squared dx. The end result is 0.95. Some of you may be wondering, where is the mu? Where is the sigma? They will cancel out. This is a definite integral. They will cancel out. And by the time you now change this guy to 3 and this guy to 3, then you're now going to have 0.997. You can try that. Now, let me tell you this. You have a chance now to earn an extra credit of 3 points. Does that make sense? Okay. Now, when your score follow normal distribution, when we standardize your score, that will also follow normal distribution. The empirical rule applies to the original random variable that follow normal distribution as well as the standardized one. That's what I'm trying to show here. Take a look at that. Initially, we have a random variable that follow normal with a mean 64.5, the standard deviation of 2.5, the empirical rule hold. After standardization, the mean is going to be 0, right? The standard deviation is going to be 1. Then we still have the empirical rule still hold. But what is going to be the difference between the two? The difference between the two is just like, the center here. The mean is 64.5 here, but in the standardized one, the mean is 0. The standard deviation here is 2.5, but the standard deviation in the standardized is going to be 1. Does that make sense? Okay. Now, I've given you a question now. Sarah is 22 and her mother hand is 65. Give me 1 second. I think I have a chat from somebody attending online. Oh, somebody said for extra credit, do we only show is for 68% or for 95? Okay. If you show for 68% and you are right, you're going to get 1 point. If you show for all the 3 and you are right, you're actually getting 3 points. So the person online, do you now understand now? The person okay, that is it. For those of you in class, it's an opportunity to earn 3 points of extra credit. Okay, now Sarah is 22 and her mother and Anne is 65 years old. Sarah scored 125 on the standard IQ test and I scored 110 on the same test. Okay, and scores on his test for the 21 to 30 age group are approximately normally distributed. Watch out for that. They've already investigated and it followed normal distribution. To be able to use this approach, your data has to follow normal distribution. Okay, Now, you have the mean, you have the standard deviation. Y-score for 61 to 70 age group are approximately normally distributed with mean 90, the standard deviation 20. Who did better? We're comparing two different age brackets. Okay, they wrote exam. This age bracket has their mean score and the standard deviation. This particular group also have both their mean score and their mean score and the standard deviation, and they are now trying to ask you a question now. You know, who did better? We don't consider mean only. Does that make sense? But we also consider the standard deviation. If you really want to compare, what we actually go to compare is standard deviation, and we can also compare their z-score. What is the meaning of z-score? That is the number of standard deviation away from the center. That's what we mean by the z-score. Hello? The number of standard deviation away from the center, if for this observation is more, okay, then it means that, there's more disparity in that data. Okay, so we don't look at the mean only. So what I'm trying to talk about is, take a look at this guy, right? This is a z-score, right? Now, what this z-score represents is the number of standard deviation away from the mean. How do we interpret z-score? For instance, if I got a z-score of 1 or z-score of -2, how do I interpret this? This guy is saying, okay, 1 standard deviation above the mean, above, because it is positive. This guy mean 2 standard deviation below the mean. Does that make sense now? But let me tell you this. Take a look at this guy. Z equal to 1, Z equal to -1. The two of them are equally distant to the center, right? Except that Z equal to 1 means 1 standard deviation above the mean. This guy, 1 standard deviation below the mean. But the fact remains, they are equidistant to the center. And we're basically going to say they are collectively called 1 standard deviation within the mean. Okay, now you know how to decide that. There's another question. Okay, here they're giving you the mean, the standard deviation now. What percentage of pregnancy lasts less than 240? That means they wanted to find the probability of pregnancy. If the number of pregnancies is denoted as X, you want to find the probability of X less than 8. Less than 240. Less than 240. And if you want to figure out that, you need to standardize. Okay. Now, when they say what percentage, of course, they're asking question on probability. How long do the longest 15% of pregnancy last? This question C here is an example of inverse normal distribution. How long do you now want to figure out X? They've already given you the probability. Okay. This is another question. You can try. Is that the tensile strength of paper used to make grocery bags is in a crucial quality characteristic. It is known that the measurement of tensile strength, of a type of paper is normally distributed. You give it a mean, you give it a standard deviation, and the purchaser of bag required to have a strength that is at least 35. What is the probability that a bag produced using this paper will fail to meet specification? Can somebody tell me, for extra credit, what do you want to find in A? They said, what is the probability that a bag produced using this paper will fail to meet specification? And they've already told you it requires at least the strength to meet certificate, to meet, the what they actually specify, specification, it has to be at least 35. Now, what is the probability that it's not going to meet? What are we finding? Look at me. Good job. That's what you want to find. Because you know what happened? Send me a message for extra credit. Okay, now, you know what happened? This is good. This is a good one. This one means at least 35. This is what they want. When the strength of that stuff is 35 or more, the quality officer is going to say, okay, that's nice. That's actually conform to specification. But the failure is going to be the complement of this guy, right? The complement of this guy is just going to be this guy. At times, we may not tell you what we can, from the statement, you'll be the one that will figure it out. Okay, so I think we have other question. Like here, among 10,000 bags, how many do you expect to fail? If you know the probability of failure, then it means you are making a prediction now. You're finding expectation now. Then you're going to use NP. The number of items produced multiplied by the probability of failure. If I basically want to know the number of failures. Does that make sense? Okay. I think I give a lot of example for you. Okay. Now, okay, I say I have some meaning. Where we are now. Do you know at times? Because it is very easy to make use to use normal distribution. We can approximate a particular distribution for normal. Like for instance, if we have a binomial question, we can use the knowledge of normal for binomial. And we're going to call that normal approximation to binomial. Because when the sample size is large, binomial distribution will be difficult to undertake. That's going to be complex. Okay, so when the sample size is large, then binomial random variable, okay, we follow normal distribution. Now, if the binomial random variable follow normal distribution, you know what happened? You know, the standard normal variable is x minus mu over standard deviation. If that happens, that mean will be the mean of the binomial. What is the mean of the binomial? NP. What is the standard deviation of binomial? Square root of NP into 1 minus P. That is exactly what we mean. But what is the requirement? We got a requirement before we can actually use normal approximation for binomial. NP must be greater than 5, or N multiplied by 1 minus P must be greater than 5. That is the situation where we can, and that was why this approximation work well when N is large and P is extremely close to 0 or 1. So you need to first investigate this guy. They must actually, they must not fail. They have to hold all the time before I can use a normal for binomial. Okay, now take a look at the question. Suppose X is binomial random variable with parameter that and that. Find the probability of S equal to 5 using binomial formula. Of course, you know how to do that. You've done that. Find the probability that S lies between that using the normal approximation. Why do I want to use normal approximation? Maybe the requirement for using that old. When I multiply N by P is greater than 5, N by 1 minus P is greater than 5. And of course, if I want to use the idea of normal for binomial, then I have to be working with, in binomial, you normally have, binomial is discrete, right? If I, 4, 5, 6. But if I want to use that idea for normal, then I'm actually going to subtract. Like, take a look at this guy now. S lies between 4.5 and 5.5. Okay. Suppose S follow binomial with this. This is the way we normally write binomial. If you take a look at this guy now, it means N equal to 12, sample size equal to 12, P equal to 0.4. Using the knowledge of binomial, you can find A. Using knowledge of normal, you can actually. Now, let me tell you this. If you want to find this one using binomial, if you now want to use the knowledge of normal, you know what you're going to do, because normal is a continuous. You know what you're going to do? Oh my God, you're going to rob Peter and pay Paul. What is robbing Peter, pay Paul? Subtract 0.5 from the lower endpoint and add the 0.5 to the upper endpoint. Do you know you are asking the same question? This is the same. This is the binomial one. To use the normal now, you subtract. It's like you are robbing the poor and giving to the rich. What is going to happen to the length? The range is going to be what? Wider. That's not good. Okay, that's not good. Don't do that. Don't do that. It's just then compare the answers. When you compare the answers will be very, very close, provided that assumption is met, NP greater than 5. So I think I gave a lot of you can. Okay, I'm not going to rush you. Oh, I think I still have 5 minutes. Now let me. I'm going to use my 5 minutes. For instance, if I want to find the probability of x less than x using normal approximation, I need a continuity correction. What I was applying the other time is continuity correction when I subtract here and I add. But when I subtract and add is when I'm talking about between. If I'm talking about less than x, I will subtract 0.5 from x. If I'm talking about less or equal to x, I will add the 0.5. If I'm talking about x greater than x, I will add the 0.5. If I'm talking about x greater or equal to s, I'm going to do minus. What am I doing here? That's a continuity correction. Why do we need continuity correction? Because I'm using normal distribution for binomial variable. There's going to be error. So that is like correcting for the error. Correcting for the error. We are adjusting. Does that make sense? Does that make sense, right? So you can take notes of all of that. So what if I'm finding between that and that? So you need this formula. This is for continuity correction. Okay, I think you can solve all that. Okay, and we've done linear combination before. It's the same as what we've done under linear combination. What is next? On Friday, I'm going to work with exponential, gamma, chi-squared, F distribution. There's a lot of probability distribution. Any question on what we've done today? Any question? Any question? Don't forget, send me your after today, latest tomorrow, 11:59 p.m. If you want to have extra credit of, based on the 3 questions, you just need to show me. If you show me that and you show all of that correctly, you're basically going to have an extra credit of 3 points. Oh my God, 3 points is a lot. Make sure you stay safe and have a lovely day. Bye for now, everyone. Yeah, the guy online. Bye. Okay.